let's see. Right, let's just see if that's started. Okay, we're now recording. So I'll just switch to the screen. Okay, so you can all see that. Yeah, guys, it should be a slide saying free energy equation.
Yeah.
And assembly. Good. So last week we considered some of the, well, last week we considered some of the fundamental properties of molecules, macromolecules, and we talked generally about macromolecular size and shape, and did a bit about units as well. I think we talked about polysaccharides a bit, and then talked about proteins and how we represent the conformations in terms of the overall shapes or conformations. So now we're going to consider some details concerning protein folding and assembly, and how that links to the free energy equation, which we introduced last week. This free energy equation, which comes from the second law of thermodynamics, it's delta G equals delta H minus T delta S. The change delta in free energy, the energy available to take part in reactions in chemical or physical chemical reactions. So delta G is a change in free energy, units joules or joules per mole, because we're dealing with a large number of molecules here, equals delta H, which is a change in enthalpy or heat energy change at constant pressure. And in many systems, we're dealing with constant pressure or near constant pressure situations. So the change in heat energy at constant pressure, change in enthalpy, minus T times delta S, where T is the absolute temperature and delta S is the change in entropy or degree of randomness of a system. And nature likes random, it doesn't like order, it likes things to be random. So if you make something ordered, then the change in randomness or disorder, this change will be negative. And negative times a negative is a positive. And so if something becomes more ordered, generally speaking, this leads to an increase in free energy. And from the second law, for a reaction to be spontaneous or proceed of its own accord, delta G must be negative. So if we're becoming more ordered, that's not thermodynamically favorable, unless it's compensated by something else which is happening. And when proteins fold, for example, although they appear to be becoming more ordered, what's happening is that favorable bonds are being formed, hydrogen bonds, electrostatic bonds, whatever. And when these bonds are formed, that results in a release of free energy. So long as this change, and when it's releasing free energy or releasing energy, the change is negative. So a release of heat energy is a negative change, delta H. So long as this term here caused by the forming of favorable chemical bonds leading to a negative delta H is more negative than this term here is positive, then that will lead to an overall delta G of negative, and so the reaction of protein folding can take place. If there's insufficient bonds being formed, leading to an insufficient amount of heat energy released, then delta G won't be negative, and so folding won't take place. So this is a good example of how important this free energy equation is, because it controls folding, protein folding. So the ability of a protein or any macromolecule, not just proteins, to fold or self-associate, that means subunits, for example, coming together to give larger structures, for example with hemoglobin, is governed by the free energy equation. So that means proteins will fold differently according to the free energy relationships, according to the bonds that are able to form. That depends on the amino acid sequence. And some may dimerize or form larger ligamers assemblies, or even interact or complex with other molecules. Or if this free energy equation dictates, stay as single molecules. Yeah. And the ability of a protein to fold not only depends on the sequence of the amino acids, but also on the environment or medium in which it is dispersed, because the medium or environment can affect the conformation, and it can do that in a number of ways. One is concentration. Two is prior heat treatment. Three is the pH or ionic strength of a solution, the local solvent environment. We say salt not in terms of sodium chloride necessarily, but in terms of general salt ions, potassium, chloride, sulfate. There could be buffer salts. So the conformation can be affected by the local solvent environment, and that involves the pH and ionic strength and the presence of any other materials in the solution. And whether the protein is in solution or a gel or in a glassy state. So all these things can affect the conformation. And a good example is the collagen gelatin system. And this table here shows the effect of different solvent conditions on the delta G. So this, we've got 4 proteins here: ribonuclease, chymotrypsinogen, myoglobin, and beta-lactoglobulin, which under normal conditions is a dimeric protein, and in different conditions. So this is low pH, so high acidic conditions. This is also acidic. pH 9, these are sort of alkaline conditions, and this is urea. Urea is an agent which can basically break disulfide, so break hydrogen bonds. So ribonuclease, so this is the data for the folding of these 4 proteins at 25 degrees centigrade. So at pH 2.5, so let's take beta lactoglobulin here in 5 molar urea. So delta G is positive. So does that mean that the protein is folded or unfolded? If the energy of folding delta G is positive.
Unfolded.
So does that mean the protein will be folded or unfolded?
Unfolded, I think.
Unfolded, that's right, because delta G is not negative. And in these conditions,
Folded.
protein will be
Folded.
Folded, that's right. So under these conditions, although when the protein folds, it becomes more ordered, and hence there's a loss of randomness. So delta S is negative in all these 3 instances, even under acid or alkaline conditions. The delta H, the heat energy change, is negative. Okay, minus 228, minus 163, minus 175. And of course, you'll need to multiply the absolute temperature. So it's T times delta S. So that's got to be multiplied by T, which is not 25, but 273 plus 25. That's 298 degrees Kelvin. And oh gosh, you think, oh, that's going to be a very large number. Therefore, that's when you've multiplied, you've got minus T delta S. That's going to be a large positive number after multiplying by minus T. And that's going to be much more than that. But don't forget, these units here are kilojoules per mole. So to convert to joules per mole, you multiply that by 1,000. And that's why for these 3 cases here, the free energy of folding is negative. So it's only in this case here that the protein becomes, or the protein remains as unfolded. Okay, so that's an example of how the entropy change and the enthalpy change, the heat energy change by the formation of chemical bonds or the disruption of chemical bonds contribute towards the free energy change. And negative net delta G means folding, and positive means the protein remains unfolded. And as we'll see again from the video by Professor David Phillips, a protein folds because it is energetically more favorable to fold than unfolded. So delta G is negative. Non-polar groups tend to be buried in the interior of the molecule, because the interaction with water is thermodynamically unfavorable, so the non-polar groups tend to be buried in the interior of the molecule. The polar groups are on the outside generally, but you can also find them in the interior of the molecule, and they can do that by forming regular structures. So they compensate their polar residues by forming hydrogen bonding between them. And the two types of regular structure are alpha helices and beta sheets. We don't find holes in the center of the molecule, not normally anyway. That is, again, thermodynamically unfavorable. Some structures can be further stabilized by disulfide bonds. There's an amino acid, or there's two amino acids, methionine and cysteine, but cysteine is the amino acid which is usually involved in terms of disulfide bonding. So you can get one cysteine binding to another cysteine residue at different parts of the polypeptide chain by disulfide bonds, and this stabilizes the folded structure. And the folding process can be assisted by chaperonin molecules. These are also protein molecules which assist the folding of other proteins, not just folding, but also assembly into larger structures. That's basically it. So in terms of references, there's that reference I showed you last time, the Garcia-Latour and Harding reference. There is this book, which is online on the Moodle. It's self-assembly of macromolecules, which are put on the Moodle for you. And now we're going to, well, after the folding clip, which I'll show by Professor DC Phillips, there'll be short videos on hemoglobin and the lysozyme structure. And then we're going to use this wonderful software called Rasmol to do our own visualization of protein structures. And you can see where the regular structures, the alpha helices and beta sheets fit in, not just in terms of single subunit structures, but also in terms of assemblies like hemoglobin. Okay, so the next thing we're going to look at then is the protein folding video again. We'll look at the hemoglobin and lysozyme videos, and then we'll use the Rasmol software ourselves. The videos by DC Phillips, I think, are really first rate. I was lucky enough to be taught by him many years ago when I did a supplementary subject called molecular biophysics when I was an undergraduate student doing physics actually. And David Phillips was, well, his group were the first ones to work out the structure, the detailed 3D structure, X-ray structure of an enzyme molecule, and that's lysozyme. Okay, I'm going to just switch off the record, and then I'll, on the chat function, I'll point you to these videos, which we'll look at, and then discuss